Welcome to Physics, Chapter 4, only sections 4.1 to 4.3, which are projectile motions. Nonetheless, this might take a little while, so grab yourself a drink and a snack and enjoy the lecture if you can. By the way, partway through, there's going to be a code word. If you get the code word and you're the first to say it to me, I think I owe you a donut. So just something to think about. All right. Projectile motion involves motion in two dimensions. By definition, projectiles have only a gravitational force acting on them. They are in what's known as free fall. Those two mean the same things. A projectile always has to be in free fall. And you might say, well, hi, Mr. Forrest, what about a projectile that's going up? It's still in free fall because it's still being acted on only by gravitational force. It could be going up, down, sideways, combinations of those, but if it's a projectile, it's in free fall. So they have acceleration in a vertical direction, and that's downward at 9.8 or 10 meters per second squared. The AP does not care which of those you use. And they have a constant velocity in the horizontal direction. Now, if there is air resistance, and we'll encounter those things this year on objects that are moving through the air, then they're not projectiles, and we have to handle them differently. One of the things we'll do in calculus-based physics is we'll learn how to use differential equations, which essentially is an equation where the rate at which a variable is changing depends on the value of that variable itself at an instant in time. A great example of that are things with air resistance, which changes depending on the speed you're moving through the air, or sometimes friction with surfaces can alter a bit when you're going different speeds, or objects that are going down through a water column, and as they're accelerating down as they go faster and faster, they have a lot more resistance to do that. All right, moving along. So when we think about an object or a body's motion, it's helpful to think of its instantaneous velocity and how the velocity is changing. So what's it doing at that instant, and is it increasing, decreasing, what have you? So the overall velocity of a projectile is the vector sum of its horizontal and vertical velocities at any instant in time. I've got to show this. I hope Mrs. Osmond showed you in AP1 this video because it's the best monkey hunter video that I know. It's a little creepy. Also, I want you to look at this example on page 89 for how to use some calculus. So the equations used for projectile problems are the same as used for one-dimensional motion. So those are like the first 3 or 4 maybe on your formula sheet for mechanics. But the vertical equations always have an acceleration in them, and the horizontal equations would have some version of this, since velocity is constant. So the AP always gives you the most generalized versions of the formula, which can be kind of annoying. You've got to decide which parts to use. So on page 95, there's some other things to know. The maximum range for a projectile when there's no air resistance and when it's landing at the same height as it's launched is 45 degrees. If those two things aren't true, this isn't true. So I think the key thing with that is with projectiles, you need to know those parameters. In other words, how is it landing versus how is it, I want to get rid of that picture, how is it being launched and so forth. If it's not being launched at the same height as it lands, then you've got to do a little bit more work. The other thing is there's this thing called a range equation, which I don't like because range means something different in math than this. It also works and is a derivation of your projectile formulas when shot at an angle to figure out the distance the projectile goes when shot at an angle and coming back to the same height, but it only works under those conditions. And honestly, the AP isn't really interested that much in equation-y stuff like this. So you could use this, but memorizing that, since it's not on your formula sheet, may or may not be worthwhile. I kind of think it's not. So I'm going to go through a couple examples. One example is find the minimum speed to cross a river when the launch ramp has an angle of 15 degrees, the river is 10 meters wide. And you don't want to go in here because there's like lots of mean crocodigators and stuff like that. So I could use this equation, though, for this, and I could rearrange it and simply get a launch speed of 14 meters per second. So there's other ways I could do that too. One would be to think about the fact that if I'm going 10 meters across, I'm going to be accelerating downward for 10 meters divided by the speed, rather. So that would tell me the amount of time that I could have, and it can get kind of complicated that way. And we'll do an example related to that in a little bit later. So example number 2, if I have a football kicked at 20 meters per second at 53 degrees above the horizontal, so let's say Tanner's kicking his football, it's kicked 36 meters from a field goal post, and the cross member is about 3.05 meters, or about 10 feet above the ground. Does the ball clear the goalpost, and is it rising or falling if it clears the goalpost? Obviously, if it doesn't clear the goalpost, it's going to be falling. So first you want to find the initial conditions. So I'm going to split this up into horizontal and vertical components. I probably should have drawn a better triangle to show you that, but I think you're pretty good with that. So I get 12 meters per second horizontally, 16 meters per second vertically. The next thing I'm going to do is I'm going to find the time it takes for the football to get to this point. So I know that the horizontal speed is going to be consistent at 12 meters per second. So I can rearrange this equation to find the time. It's going to take 3 seconds to reach that field goal post. So now I can find the vertical position after 3 seconds and the vertical velocity after 3 seconds. So the vertical position is a version of this formula. I'm initially going upward at 16 meters per second, but I'm accelerating downwards at 9.8. Again, if you use 10 meters per second squared is your acceleration downward, you get a slightly different answer. So when I do this, I get that after 3 seconds, I'm at 3.9 meters, so I would clear the bar. Woohoo! The field goal is good. Probably we know it's going to be declining or going down at that point, but we want to take a look anyhow, because 36 meters would be a pretty long field goal. Probably about over 40 yards for sure. So we could use this formula to figure out whether our ball is rising or falling at that point. So A is equal to dv over dt, or delta v over delta t. And I know my initial velocity is equal to 16 meters per second up. I know that I'm accelerating downward at 9.8 meters per second squared for 3 seconds. So I get that my final velocity is 13.4 meters per second downward. So it's falling pretty fast when it clears the goalpost. So it didn't clear it by much. Sample number 3 I think is an interesting one. I'm going to include the PDF with this. And I might make this a little bit smaller so you can see more of it at a given time. So we've got a motorcyclist, and they want a 3-second flight time while jumping across a gorge, 60 meters across. This person will land at a height 15 meters below where they launch. So we want to find the correct angle of launch, that's here, the correct launch speed, the correct angle for the landing ramp, and the predicted landing speed. That's a lot of stuff for basically only knowing that this is 60 meters across and this is 15 meters too high, or higher than this side. So it seems like we don't have nearly enough information for what we want to do. So, with that being said, first of all, I think I can find the horizontal velocity, because if I want this to take 3 seconds, and I know that the horizontal velocity doesn't change, I know that I'm going to cross 60 meters in 3 seconds, so that gives me a horizontal velocity of 60 meters per second. Now, what I find really useful here is to compare this situation to one with 0 gravity. So if there is gravity, my path will look something like this black dotted line. But if there's no gravity, I've got something which will look like this dashed dotted line in green. So without gravity, the motorcycle will go at a straight angle up into the sky. Well, the question would then be, once it reaches this spot, how far would it fall in 3 seconds to land at this spot? So how far could it fall in 3 seconds? Well, if I use this general equation, and I guess it should be a delta y instead of an x, but that's the general symbol that I'm using, it could fall 44.1 meters compared to if there was no gravity, and it would still hit this part of the hill. Now, if I think about that, it's falling 44. It can fall 44.1 meters, but part of that's because this is 15 meters below where it launched. So in reality, if I look at this and compare it to the launch height, it can fall 29.1 meters compared to the launch height. Well, what good does that do? What it does is it lets me know that for the 60 meters across, my motorcycles can fall 29.1 meters compared to where they would be with no gravity. And that lets me know that the angle at which they'll be launched, 29.1 over 60 meters. That actually got me part A. To find the correct launch speed, well, I know the angle now. I knew my horizontal velocity was 20 meters per second, and I can go back and figure out my overall resultant velocity. I could do the cosine of 25.9 degrees equals 20 over VO. And to rearrange that, I get 22.2 meters per second. So now I've solved for part B. We could also find the initial vertical velocity by using the other side of this, either tangent or Pythagorean theorem or whatnot. And it says that its initial upward speed is 9.7 meters per second. Now to find the final vertical velocity, it's not going to just be 9.7 meters per second because we're ending up lower than where we started. So how could I figure that out? Well, I could use this formula, which is basically A equals dv dt over dt, and I could figure out my initial velocity, which is 9.7 meters per second upward, my acceleration, which is 9.8 meters per second squared downward for 3 seconds, and I get that my final downward velocity is 19.7 meters per second down. So, if my horizontal velocity is constant at 20, my final vertical velocity is 19.7, and this lets me know that I'm going to end up with a final speed of around 28 meters per second and around 45 degrees below horizontal, since these are about the same. And then the last part is, essentially this angle here was actually part C, and D was the landing speed, sorry. So in the back of your book, it's asking you to find the maximum, and this is problem number 39, it's part A, it's a derivation, finding the maximum height of a projectile launched from a vertical velocity VO at an angle theta. So if we think about the vertical velocity as being VO sine theta, the horizontal velocity being VO cos theta, the maximum height, the vertical velocity would be 0, the horizontal velocity would still be the same. So the time to get to the top, since we're looking at dv dt as acceleration, we could say is VO sine theta minus 0, and A is g. If I rearrange this, say that t is equal to delta v over A, or t equals delta v over g, so that's the time to get to the top of the path. So that's an interesting derivation there. The time to fall or rise to a maximum height can be found with this. And again, we know that 1/2 g and this squared, we could say, wait a minute, that's time. We just figured out time. So 1/2 at squared would be 1/2 g. This is time squared. So we get something that looks kind of complicated, but we really put these two formulas together. So we started out with a base formula here and a base formula here, and we came up with something that looks completely weird. And that's a little bit how we get that maximum horizontal range also, which is the formula that I mentioned earlier, which was back here. Okay, so hopefully those are some good examples. I think you know how to do projectiles pretty well. AP usually doesn't have a straightforward projectile problem, but they'll put it as part of something else, like a momentum problem or an energy problem. So again, hopefully those help. Oh, the magic word. The magic word is winning record. That's a magic phrase. Browns have the first time since before you were born that they've got a 3-1 record. So winning record.